On Zoom. Get the boards on in view. Okay, so now we're talking about the modulus and the argument of a complex number. So modulus just means the size of it, how big is it, and the argument is the angle that it makes with the real axis, the direction that it's going to have. So we're going to calculate both manually, and then I'll show you a skill we can use on our calculator to determine. So we have -1 take 2i, we're asked to find the modulus of z. So the modulus of z is going to be the square root of the real component squared plus the imaginary component squared. And when we say the imaginary component, all I mean is the coefficient of the imaginary component. So this is going to be the square root of 1 plus 4. The modulus of z is the square root of 5. Now, for the argument of z, I'm going to just to talk about what does it mean. Like we're saying, what direction does it go in? So if you were to draw this number on the complex plane, we're going across 1 and then down 2i, so it's going to be to here. And so the argument of z then is this angle here. All right, we have this restriction for the argument of z. We define it between minus pi and positive pi. So from minus pi the whole way around to positive pi. So we want to determine this angle here. The way I'd be doing that is abstracting this triangle that we have. And I know that this side is 1 and this side has a modulus of 2. Okay, that's 1, that's 2. We can determine this angle, phi, all right, using trigonometry. This is a right angle triangle. This is our hypotenuse, opposite and adjacent. We've got O and A, so it would be tan of phi equals O on A. So tan of phi equals 2. So phi is inverse tan of 2. Now, we're going to do that in radians because we've defined our angle in radians, right? So I'll evaluate that quickly in my calculator. And so what I'm showing you here is a long way of doing it, but showing you how it's sort of defined and so forth. So I'll go shift tan of 2, and we've got 1.107, 1.11. Okay, so that means that this angle in here is 1.11. And so my angle theta, well, half a revolution is pi, so my angle theta is going to be pi, take away 1.11, 3.14, take away 1.11, 2.03. Okay, so that's our angle theta. Now, that's the size of it, but because it has direction, we need to put this negative in front of it. It's in the negative direction. It's going below. We're rotating anti-clockwise from the real axis. All right, so that's how we can get it, making a sort of manual argument. Let's go to our calculator. So if you can pull your calculator out. All right. And go to your run mat, and I'll write some instructions. Here, I'll write this out. We have option complex. Okay, and you'll notice in there, you've got absolute value and you've got argument. All right, so if we type in, if we press absolute first, and then we can type in the complex number that we had, which is -1, take away 2. Now there's 2 places we can bring up I. I should now correspond with F1 when we're in complex mode. We've got I at the top. You've also got it at the bottom. If we press Shift 0, that's going to bring up I as well. Okay, and we can see that brings us our root 5. And similarly, we'll do the same thing for the argument. We want the argument of. You need to use brackets, the argument of, and then we type in -1, take away 2i. Close our bracket. And I've got -2.03. Okay, so we can use our calculator. This is what we're going to do all the time. This is just a bit of theory as to where those 2 things come from. All right. If you have questions about the calculator, I'll come around and ask them. Okay, let's move on to 2 then. Sketch this zone. We want to sketch a complex number such that the modulus is always larger than 3. So if you think about, here's the complex plane. And here's a circle that has a radius of 3, And we have a set of complex numbers such that the modulus of it is always larger than 3. So we're going to shade the region outside this circle. Okay? This whole region satisfies the statement, the modulus of z being larger than 3. Okay? Similarly, we're restricting, we don't have a restriction of the modulus of an argument, and same with that one, that would go on forever. We're restricting the argument, so here we have pi on 2, and here we would have 2 pi on 3. Whoops. That's going to be 2 pi on 3, so we're restricting the argument to this region here. Okay, we've got a proof. We have the modulus of z times the modulus of w equals modulus of zw. So this one here, I want to really be clear to you how I would like you to perform proofs, okay? So whenever we have a proof like this, we need to somehow define these z and w complex numbers. So let's do that first. Let z equal a plus bi, and let w equal c plus di. Alright, so we've got these two complex numbers. And then what we're going to do is we're going to start with the left-hand side and manipulate it and see if we can get it to match the right-hand side. So left-hand side is equal to the modulus of z times the modulus of w. So that's the modulus of a plus bi times the modulus of c plus di. Okay, so we put it in the modulus formula, and then I extend the square root over to both, because the square root of a times the square root of b is the square root of ab. That's a law of surds. We'll perform some FOIL here. We'll have a squared c squared plus a squared b squared plus b squared c squared plus b squared d squared. And there's really nothing else we can do there. We've just expanded the left-hand side. Okay, which means we've got to manipulate the right-hand side. We've got to show that the right-hand side is equal to the left-hand side at some stage. So I'm going to jump on the right-hand side. I have the modulus of zw. So that means first I'm going to multiply z by w. Alright, so we'll have AC, again we're doing the FOIL, AC plus ADI plus BCI plus BDI squared. Alright. Now BDI squared becomes take away BD, so I'm going to separate this into the real part. That's the real component, AC take away BD, and then plus the imaginary component. And now we're going to perform the modulus of it. So the modulus says we have the square root of the square of the real component plus the imaginary component. Okay, everyone okay so far? Alright, so then we've got some perfect squares to perform. So we've got AC squared, take 2ACBD plus BD plus B squared D squared. And then we have over here plus, we'll have A squared D squared plus 2ADBC and then plus B squared C squared. Alright, those are like terms will cancel, and we're left with the left-hand side. Equals left-hand side QBD. Alright, so the main thing I want to point out with proof right, is we start with the left-hand side, we mash it until we can get the right-hand side. We can't really get the right-hand side straight away. So then we'll jump over to the right-hand side, we process it, and we've demonstrated that from the right-hand side, we can illustrate it's the same as the left-hand side at this step. Okay, they are the same equation. All right. So what did we do? We defined A plus BI, and then we just matched this side. Here's what we end up with. We defined it, and we matched this side, and we processed and processed and processed, and we end up with the same. So it's true. Okay, here we are. This is like a problem-solving one that we're going to have. Find the modulus of z, given the modulus of z plus 16 equals 4 times the modulus of z plus 1. Now we're going to use a property here, which is the modulus of z squared is equal to z times the conjugate of z. Okay, so the properties of modulus are listed at the top, in the middle box of 4b there, you can see. So we're using the second dot point one. All right, so the first thing we're going to do with this equation is square both sides so that we can use this property. All right, so if I square both sides, what will we have? This will become 16. So we'll have z plus 16 squared equals 16 z plus 1 squared. Okay, so we're treating that whole thing as the modulus of z squared, so we can write it like this, z times the conjugate of z. So it's going to be z plus 16 multiplied by the conjugate of z plus 16. Okay, that's what's going on the left-hand side. And on the right-hand side, that 16 is just going to hang out, and we'll have z plus 1. We can get rid of the modulus now, multiplied by the conjugate of z plus 1. Now, if I can just describe z plus 16 conjugate, okay, if we just focus on this part, it's equal to the conjugate of z plus 16. All right, and the reason is the conjugate of a real number is just a real number. It doesn't change its value whatsoever. So if you think, like if I had, let's just paint a real circumstance, if I had 2 plus 3i, all right, this is the, so let's say that's complex number z, and then we have plus, we can put 16 there, I've got z plus 16. If I'm performing the conjugate of this, the only part that changes is the imaginary component, okay? So that means the conjugate of z plus 16 is just the conjugate of z plus 16, all right? All we're doing is adding on our 16. So we'll have z plus 16 times the conjugate of z plus 16, and we'll have the same thing over this side. We'll have z plus 1 multiplied by the conjugate of z plus 1. Okay, on the left-hand side and the right-hand side, we're just going to expand. So here we won't have z squared, but we'll have z conjugate of z, and then we'll have just FOIL 16z, 16 conjugate z, and then 16 times 16. 256. And then here that 16 will stay up front for now, ZZ. Okay, we'll distribute this 16. Start to see we've got some stuff that's going to cancel. So we've got positive 16z on the left-hand side and the right-hand side, that will cancel. We've got 16 conjugate z on the left-hand side and the right-hand side, that will cancel. I'm going to move this 16 over to the left-hand side, so 256 take 16 will be 240. And I'll move this z conjugate z over to the right-hand side, which will give me 15z conjugate z. Divide both sides by 15. Give me 16 equals z conjugate z. And z conjugate z is the modulus of z squared. So modulus of z is 4.
Would it be plus or minus 4?
Nah, because it's modulus, it's sized.
Yeah. Oh yeah, because it can only be positive size.
Good. Excellent. Okay, so there's a little bit more involved in this exercise. So that's 4B. Yeah, let's get into that. That'll probably be where we just dedicate our efforts today. If we want, we can move on to C.1, see how we're going.